Hey everybody, in this next video lesson we're going to talk about fission and fusion and also nuclear reactors. We're going to start talking about fusion. As we talked about in the last video lesson, the goal of fusion is to combine two light nuclei to form a heavier, more stable nucleus. That way it can achieve a more stable nucleus and move closer to that iron value, that being the most stable nucleus of any nuclide that we know of. This is happening in stars all the time. Hydrogen is combining with another hydrogen to produce helium and a loose neutron. These two hydrogens are not your normal hydrogen. Normal hydrogen has one proton and zero neutrons, and so its mass number would be 1. But this is called deuterium, which has an extra neutron. And this one's called tritium, which has 2 neutrons or a mass number of 3. These do occur, but they're not the most common forms of hydrogen. This process requires a lot of pressure and very high temperatures. This is very difficult for humans to do on Earth, because it requires a minimum temperature of 40 million Kelvin in order to initiate fusion. And we can't do this with just anything. The only way that we have seen fusion work is using a hydrogen bomb, which actually requires the use of a fission reaction, which we'll talk about in a few minutes, to initiate a fusion reaction. And so in order to achieve this temperature, we need to have fission first before we can have fusion. Because of this, it's fairly impractical to do fusion here on Earth. The only way this ever happens is on stars or inside stars as they convert hydrogen to helium and even higher mass elements after that. The next one we're going to talk about is fission, which can be done at much cooler temperatures and generates an extreme amount of energy, which we have used as nuclear power plants, but we've also used for destructive purposes in nuclear bombs. Fission is the splitting of a heavy nucleus into 2 nuclei with smaller mass numbers. So an example of this is uranium-235, which is the fuel source for most nuclear power plants and nuclear bombs. What happens is a neutron gets shot at a uranium-235 nucleus, and if it's traveling slow enough, it will absorb to become part of the nucleus. Now this nucleus is much less stable and will disintegrate very quickly and release 2 daughter isotopes, barium and krypton, and in the process send out 3 loose neutrons. Now, if there's more uranium-235 around for these loose neutrons to attach to, well, this reaction will happen again, and then again and again in what is known as a nuclear chain reaction. If that's done in a controlled way, you can run power plants. But if that's done in an uncontrolled way, well, that can cause catastrophic failures of power plants and also produce nuclear bombs. In addition to the daughter isotopes and the neutrons, an incredible amount of heat is generated and also a lot of gamma radiation, which is radiated off from this process, which makes this such a dangerous situation for humans to be around. At this point, I'm going to splice in a little video clip from a different video lesson that I recorded for a different chemistry class that takes us into a computer simulation and shows us 3 situations in which fission are applied. Check it out. All right, here's a little computer simulation that I'm going to show you. We'll take a look at nuclear fission in a couple different stages. This first one is just going to show you basic nuclear fission. This little gun is going to be able to fire 1 neutron at a uranium-235. It's green uranium-235, which means it's fissionable material. And when I fire the neutron, it becomes 236, and then it splits. And as you can see, it releases 3 neutrons in the process. Let's do that again. It absorbs the neutron, gets super unstable, decays, and 3 neutrons get thrown out. Let's talk about nuclear chain reactions now. So I have set up a situation where I have a mixture of uranium-235 and uranium-238, and once again I got my little neutron shooter. Now uranium-238 is not fissionable, and if you get it hit with a neutron, it's just going to turn to uranium-239, and that's going to be basically just nothing. Nothing's going to happen. But if one of those neutrons hits a uranium-235, well then it's going to split off and it may strike another uranium-235, as you saw, which may cause another uranium-235 to explode. But if those neutrons get hit by uranium-238 or they run into a uranium-239, well then nothing happens and there's not a chain reaction. But what I can do is reset this situation and reduce the amount of uranium-238 and have a higher concentration of uranium-235. This is what is known as enriched uranium. And if you have enough enriched uranium, then you can basically have a chain reaction that causes more uranium to explode because there's less uranium-238 to absorb those neutrons, those loose ones that get shot off. Well, that didn't really react much of my uranium-235, so let's reset and take even less. Let's aim my shooter up here and see if I can get all of these to explode. Loose neutrons just happen to not hit any of these in the bottom, and so let's reset my nuclei and let's add more nuclei to the mix. So if I can pack a higher concentration of nuclei and shoot a neutron, maybe I can get all these to react. So there you go. Each one of them strikes another nucleus, causing more chain reactions. Now let's fill this thing up with 100. And here it goes. And as you can see, all the fissionable material has been used up. But I can slow down the chain reaction if I mix in a little bit of another uranium isotope, uranium-238 or uranium-239, and it will stop the chain reaction from happening. Now, another way to stop the chain reaction is in a situation like a nuclear reactor. Now, the reactor core has basically little pockets of fissionable uranium-235. And as you can see, I'm moving these control rods. Now, what happens here is if I don't have the control rods and I fire the neutron, you're going to get chain reaction, kind of like we saw in the last slide. All the uranium will fire off, releasing its neutrons, and the chain reaction, as you can see, is moving from right to left. But I can slow this down if I add these control rods in, and it will basically stop or isolate the chain reaction to just one pocket of this nuclear reactor core. So I fire the neutrons again, and not much happens. I can fire them again, a little bit of action over there on the left, but everything stops. But if I can basically move these control rods, what these control rods do is actually block or soak up any loose neutrons to keep them from reacting with other uranium material. And the control rods are the same way that nuclear reactors control a nuclear reaction, by moving them in or out. The further out, the more nuclear reaction occurs, and the further in, the less nuclear reactions occur. And so you can control how fast the reaction happens by adjusting the control rods in or out. Now, if you have the control rods all the way out, you may cause a runaway chain reaction, which might produce so much heat that it melts down the reactor core and blows the top off your containment vessel, and the containment vessel then spews radioactive material into the atmosphere. So the control rods are a really, really, really important component of a nuclear reactor core. They control how fast a nuclear reaction goes. I hope that computer simulation was enlightening to you, and you know a little bit more about how fission reactions work. The mass of the fissionable material has to be large enough to sustain a chain reaction. And I showed this in that computer simulation. We call this a subcritical mass when the amount of fissionable material is either not concentrated enough or too far spread out, or maybe interfered with different isotopes of uranium, which don't allow the neutrons of one decay to reach the neutrons of another potential decay situation. So we call this a subcritical mass when the rate of the neutron loss is greater than the rate of the neutrons created by fission. And so this is an example of when a nuclear reaction fizzles out. Think about that last part I showed you with the control rods. When the control rods are completely shut, the reaction fizzles out because you lose the ability of neutrons to hit other uranium-235 isotopes, and the reaction just kind of stops in its spot. Now, on the other end of the spectrum, you've got the supercritical mass, which is when the rate of the neutron loss is less than the rate of the neutrons created by fission, and what happens there is an explosive chain reaction. This is an example of when I had the entire picture saturated with uranium-235, and I just sent one neutron, and within a matter of seconds, every uranium-235 was completely destroyed by neutrons hitting other 235, and it just completely, it's called a runaway chain reaction, and that is when you have a supercritical mass situation. Now, somewhere in between, where you've got just the right amount of neutrons being lost to neutrons being created, well, you have what is known as the critical mass. In this case, the amount of energy released is a nice slow process. It doesn't get too hot because it doesn't increase, the chain reaction doesn't run away. It simply just sustains at a nice pace that is controlled. And this is a situation that's ideal when you're talking about things like nuclear power plants. And that's the whole point behind the control rods, is that you can put them in or out so that you can maintain a critical mass and not have your nuclear reactor melt down. This is what happened in Chernobyl back in 1989, but we'll talk more about that in a little bit, where there was a malfunction of the control rods and the uranium was able to get too much fission going on, and as a result, it boiled the water, exploded the top, and released all that radioactive material into the atmosphere. We're going to finish up here talking about nuclear power plants, and this is a schematic of a nuclear power plant. Now, nuclear power plants are considered green energy because they do not release carbon dioxide into the atmosphere, which could cause climate change and global warming. But the downside to nuclear power plants is that once the nuclear fuel is used up, all of the used nuclear fuel, which is now called nuclear waste, it's going to maintain its radioactivity for many thousands of years. And so we can't just like throw it around or bury it underground where people are going to come in contact with it, because it could be very dangerous for a very long time. And so there's some pros and some cons to nuclear power plants. But let's take a look at how this works. Basically, what a nuclear power plant is a set of 3 interconnected rings, all performing a slightly different job. We'll start here in the reactor core. And so the yellow stuff that you see is the fissionable material. This is the uranium-235. And those are interacting with each other and producing heat, and the heat is warming up water, and that water is being cycled through, constantly cycled, through a loop and coming back. Now, the control rods then get lowered in place to either slow down or stop that nuclear reaction from happening, and they can be released or pulled out if you want to increase the amount of fission going on and increase the amount of heat. And so the control rods are basically running the show here. The uranium is going to decay regardless as if the control rods are in place or not. Problem is, or the way the control rods work, is they can slow down the reaction that happens between different reactor cores or different reactor cells. Now that hot water then is cycled through, and the heat from that hot water in the reactor core is then used to transfer to the heat of a different water vessel, which then converts it to steam. The steam is pumped through a turbine, and the electricity is generated in this second part of the nuclear power plant. Now that water is then condensed, reformed into liquid, and pumped back through. So this is also a continuous cycle. This is where the heat from the nuclear reaction is transferred to the water, which is then used to run the steam turbine. Now a third loop is then introduced on the tail end, which is designed to cool down the water inside this second loop. So if the water gets too hot, it will boil, and if it boils too much, it could explode and also cause the power plant to go into a serious situation, a serious meltdown problem. And so this third loop's job is to continuously pump even cooler water that goes through the second loop, which the second loop goes through the first loop. Now sometimes this is just a lake or a river, large water source, but oftentimes this is a large tower of cooling water, which is the signature picture in your mind of a nuclear power plant. It's those cone-shaped concrete things sticking up into the air that are often just filled with water, and their whole job is to absorb heat energy from stage 1 and stage 2 of the nuclear power plant situation. Now the reactor core is housed inside a containment shell, which is many meters thick of concrete and lead. Oftentimes, it is sealed completely shut so that if there is a breach of the reactor core, all that radiation doesn't make its way into the general public, and even buried underground so it doesn't seep down and get into the water supply. But if you bust a hole in the containment shell, which happened in Chernobyl, then you have a serious problem, because all that radiation coming from the reactor core is then spewing out into the atmosphere, which can cause some very serious and very considerable health concerns. To this day, you cannot live within a certain number of miles of Chernobyl because it continues to be radioactive due to the accident back in 1989. If you're interested in learning more about Chernobyl, I strongly recommend watching the miniseries that was created on HBO, which is based on true events. It is fantastic. We're going to finish this video by taking a close-up look at the nuclear core And as you saw earlier, we've got the uranium fuel cylinders here all being suspended in water. And in between each one is the control rods, which absorb the neutrons when they get released from the uranium. And so if you want more reaction to happen, you pull the control rods out. And if you want less fission happening, then you put control rods back down. All the while, the coolant is continued to be circled, and it gets hot out the top and then comes back in as a cool state. And if the pumps stop working, then the water doesn't get circulated, then this water boils, explodes. That might explode then the containment cell, which is exactly what happened in Chernobyl. In that situation, the reactor control rods got stuck up at the top, and the inside of the reactor core got way too hot. And they call it a meltdown because it gets so hot that the uranium begins to liquefy, pool up on the bottom, and then you're pretty much screwed at that point. It's going to continue to react, and since it's a critical mass, it now becomes a supercritical mass because all of those fuel cylinders become condensed down on the bottom, and then that's just going to continue to burn for many hundreds and thousands of years, as it is right now. Currently at Chernobyl, they have a football field size concrete shell that has been moved in on train tracks that is completely covering this. But to this day, the reactor core continues to react and will do so for many hundreds, if not thousands of years. The other example of a nuclear disaster was the Fukushima power plant in Japan after the tsunami 10 or 15 years ago. In that case, after the tsunami hit, it disabled the water pumps so the water could no longer be cycled through, and because of that, then it boiled just like in Chernobyl. The top blew off the reactor core and released all of that radioactive material into the air. Well, that takes care of this video lesson on fusion and fission. Thanks for watching.